Hey guys, this is Carrie, and this is lesson 4 from Unit 11. So if you haven't yet, pause now and try the do now. Okay, cool. So taking a look at the do now together, we've got 3 angles that we need to graph in standard position. And so standard position always starts with the starting side of the angle on the x-axis, and it opens counterclockwise. So we're going to open counterclockwise here. That would be 90 degrees, but we want to get 260, so we've got to go a bit further. 90 more would be 180 degrees. 90 more would be 270 degrees. So we don't want to get all the way to 270 degrees. We want to get to 260 degrees. So you don't have to show that as 3 separate angles. I was just showing that as I was figuring it out. So here we go. This is what a 260 degree angle looks like. And that ends in quadrant 1, 2, 3. That ends in quadrant 3. And so we call this the terminal side because terminal means ending. All right, so now we need to graph negative 145 degrees. And because it's negative, it's going to go the opposite direction. So instead of going counterclockwise, this one is going to go clockwise. Okay, so we start here. This would be 0 degrees. If we go clockwise, this would be negative 90 degrees. Another clockwise 90 degrees would be negative 180 degrees. So we don't want to go all the way there. We want to go, it looks like partially there. So negative 145 degrees would be something like this. And our terminal side is once again in the 1, 2, 3, 4. It's in the third quadrant. For 888 degrees, this angle is huge. So we're going to do one full circle. That's 360 degrees. If we do another full circle, that'd be another 360 degrees. That'd be 720 degrees. So we have to go around, well, let me just redo that, sorry. You go around once, you go around twice, and then you have, out of the 888 degrees, you've accounted for 720 of those degrees in your 2 full rotations. So you're left with 168 degrees. So going 168 degrees from here would be 90, and then another 90 would put us at 180, but we only want to go 168, so we're going to be like here. So here's our 888 degree angle. So this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So quadrant 2. Okay, so now that we know how to graph these angles in the coordinate plane, how do we connect these ideas with sine, cosine, and tangent? So remember, whenever we're trying to find the sine, cosine, and tangent of an angle, we write it so, toa, in order to help us keep track of what ratios these actually represent. So I don't really see a triangle in this picture off the bat, but if we're thinking about it, graphing this point would mean we go 48 units in the x direction and then 55 units in the y direction, meaning that we really do have a right triangle here. In fact, we're missing one side of the right triangle, which is the hypotenuse here. And I'm not going to call it x because when I say x, I think about the x coordinate, and when I say y, I think about the y coordinate. So maybe a good name for this, oftentimes in physics class or math class, we call distances between things radii between things. And this is actually, I'm using an R here for radius, and this is actually a good word to think about when it comes to angles. Because kind of what you have here is you've got a radius that's spinning around. Well, that's the worst circle ever. Whoa. You've got a radius that's spinning around here. Oops. So it's like you have a radius and then it's spinning around. And so depending on where that radius ends up, that's going to be your angle. But I'm going to call it R. Long story short. Okay, so to find R, we're going to use the Pythagorean theorem. So we'll do a squared plus b squared equals c squared. We'll do 48 squared plus 55 squared equals r squared. And I haven't done either of these calculations, so let's go over to Desmos. And we'll do 48 squared, and we'll also do 55 squared. That's 2,304, 3,025. 2,304, 3,205 equals r squared. Now we need to add these together. So 2,304 plus 3,025, that's 5,329. And then finally we need to find the square root of both sides to solve for r. So r is equal to square root of 5,329. 73, great. That's nice that it's a nice number. So the radius is 73. Visually that makes sense. The hypotenuse should be the longest side, and it is. All right, so time to figure out our sine, cosine, and tangent. So we have our focus angle here. So that gives us our opposite from that, our hypotenuse, which is the radius, and then the adjacent is the one remaining side. So using these, so sine is opposite over hypotenuse, so 55 over 73. Cosine theta is adjacent over hypotenuse, so 48 over 73. And tangent is opposite over adjacent, so 55 over 48. And we've got sine, cosine, and tangent completely defined, so that's perfect. All right, continuing on. So we've seen this type of thing a lot in the last lesson and this lesson so far. But the last problem in the last lesson was this key idea, which is rather than use numbers, let's start to use variables to make things much easier to work with. So we've seen that if a terminal side of an angle lies in the first quadrant, then the following diagram will apply. So as shown in the diagram below, a point with coordinates x, y lies on this terminal side. This point is a distance r from the origin. And now I think we know why we call this distance r. It's like the radius from the center out to that point. And let's label some of the other things. So we don't have a right triangle yet, but we're about to. We go x units in this direction and y units up. So it looks like for this angle, because we're using letters, let's write out so, ka, toa. Sine of our angle is going to be opposite over hypotenuse. So it looks like we'll have y over r. So sine of theta is y over r. Write a similar equation that gives the value of cosine of theta. Well, cosine of theta is going to be, let me switch this to pink. Cosine of theta is going to be adjacent over hypotenuse, so x over r. And tangent of theta is going to be opposite over adjacent. So tangent of theta is y over x. And so what we have here is we have three formulas that are exactly equivalent to these formulas. They come from these formulas. Sine is opposite over hypotenuse, adjacent over hypotenuse for cosine, and tangent is opposite over adjacent. But instead of framing things as sides of triangles, we're framing things from a coordinate perspective. So we have, instead of SOHCAHTOA, we've got a mnemonic that's kind of impossible to say, but we've kind of updated our trig formulas so that instead of having this idea of being trapped in a triangle, now we have formulas that work for the coordinate plane, because any point will have a y coordinate, an x coordinate, and a distance. So we're going to see in a second that these updated definitions actually are super helpful. So instead of thinking about sine of theta as opposite over hypotenuse, we're going to now start to think about it as, well, opposite here was always y, always the y coordinate opposite over the radius. Cosine was always adjacent, which always happened to be x over r. And tangent of theta was always opposite over adjacent, which in every case was always the y coordinate divided by the x coordinate from the last two lessons. So we have this wonderful idea. Because these ideas are always true for angles in the first quadrant, we can extend our understanding of sine, cosine, and tangent to angles so large that they extend out of the first quadrant. And the way we're going to do this is we're going to say, instead of using the triangle formulas, I'll actually write the word out, sorry, triangle formulas, which are SOHCAHTOA, use the coordinate plane version. And since these are the same for angles in the first quadrant, this is like an updated version of sine, cosine, and tangent that lets us handle big angles. And I'm just writing these three formulas with some very shorthand notation there. All right, so let's see this in action, because this is somewhat esoteric before we can actually apply it. All right, so write the three formulas. Oh my gosh, I keep doing this. Sine theta is y over r. Cosine theta is x over r. Tangent theta is y over x. And I have these really memorized because they're super useful. They're actually more useful kind of in the long run than the previous formulas. And the reason why these are so useful is if we look at all of these angles here, we can actually find their sine, cosine, and tangent. So even though this angle is way too big to fit in a triangle, we know that the sine of theta, oh, actually, let's just label the r value first. I'm going to switch colors for a second. R value is 29. We know that the sine of theta, well, we can't build a triangle, so we can't use SOHCAHTOA. So our only option is to use our new formulas up here. So we know that sine is the y coordinate divided by the r coordinate, or the r value. So negative 20 divided by 29. And notice that we take the sine with it. Cosine of theta, that's the x coordinate divided by the r coordinate. So 21 over 29. Tangent of theta, that's our new formula. That's the y coordinate divided by the x coordinate. So negative 20 over 21. And we are able to find sine, cosine, and tangent for this one. For the next one, we can't build a triangle. This angle is too big to fit in a right triangle. So what we're going to do is we're going to use our updated formulas right here. Sine of theta is equal to y over r. So labeling r on the graph, 25 here, we get y over r, 24 over 25. Cosine of theta is going to be x over r, so that will give us negative 7 for x over 25 for r. And tangent of theta is going to be y over x, so that will be 25, sorry, not 25, y, 24 over negative 7. And it's common that when you have division by a negative sign in math, you write it as the negative sign out front, so negative 24 over 27. And it's amazing how these new definitions allow us to find the sine, cosine, and tangent of angles that couldn't fit in triangles. What's important to remember is these definitions, they really come from the picture that you guys constructed for checkpoint 4 in the last lesson, and that we just reconstructed from problem number 1. All right, so please do the rest of these on your own. Did I not make checkpoints? Oh, here they are. Wow. It's going a long time before we get to checkpoints. Okay, so please do these 4 on your own, and we'll come back and check them. So I think in particular, E is pretty interesting to look at, because here both coordinates are negative. So here r is 5, this is x, this is y. And so we're going to use our new formulas. Instead of opposite over hypotenuse, there's always the y coordinate over the r coordinate. Cosine was always x over r, and tangent was always y over x. And so y over r gives us negative 3 over 5. Cosine theta was negative 4 over 5 because it was x over r. And tangent of theta is y over x, so negative 3 over negative 4. And this is why we did this one. Negatives cancel out here because we have a negative divided by a negative, and that just gives us 3 over 4. So this is a pretty awesome extension. It lets us find the sine, cosine, and tangent of any angle in the coordinate plane. Let's continue on. All right, so theta is an angle whose terminal side is in the 4th quadrant. If tangent of theta is negative 24 divided by 7, then which of the following is the value of sine of theta? What is the value of cosine of theta? So it's very useful when you have problems like this that you draw a picture. So we know that our angle is going to start at the same starting place as always. It's going to end in the fourth quadrant, so 1, 2, 3, 4. So we know our angle is going to end here somewhere. Now that's going to have some x and y coordinates. It's going to have a radius as well. So let's see if we can fill those in. And to fill those in, because this angle theta is way too big to fit in a right triangle, we're going to use our updated definitions. So sine is y over r, cosine is the x coordinate divided by r, and tangent is the y coordinate divided by the x coordinate, opposite over adjacent. So that's where those are coming from. All right, so here we go. Tangent is supposed to be y over x, so we know that this is going to be y and this is going to be x. Now the one challenge that we have here is, after putting 24 and 7, we know that because the whole fraction is negative, it means that one of our values, either y or x, is negative. And the only way you can tell which is negative is to use the graph that you drew. So if you think about graphing a point here, this point right there, you're going over and then down. So is x positive or negative? Well, you're moving to the right, so x is a positive number. So that's positive 7. But because you're going down 24 units, y has to be a negative number. So I'm going to make that a blue negative so that it doesn't get lost in the mix here. Negative 24. All right. And then next up, we need to find our radius. And so our radius can be found the exact same way that we found it before. We use the Pythagorean theorem because our triangle has side length 7. And even though we're going down 24, it has a length of 24 down. So we're going to do a squared plus b squared equals c, or radius squared. And so we'll do 7 squared plus 24 squared equals r squared. 49 plus 576 is equal to r squared. 625 is equal to r squared, and r is equal to 25. And I think this is the same calculations that I sped through in the last lesson. It's a really common set of 3 numbers. That's the reason why we can do these really fast. Also, I just skipped a step. We took the square root here. So r is 25. Okay, so sine of theta. We got to go back to our definition. Sine of theta is y divided by r. So we'll do y divided by r. We get negative 24 over 25. And the same way that we saw before, if the top is negative, it's the same thing as the whole fraction being negative, because negative divided by positive makes the whole thing a negative. So then for cosine of theta is equal to x. Oop, I shouldn't circle the sides of the triangle. X from the coordinate here, x over r, so 7 over 25. And notice that both of these are positive because x is positive and r is always positive. R is a distance. So here we go, 7 over 25. All right, let's do one more of these because these are a little bit complicated to get the hang of. All right, so theta is an angle whose terminal side is in the third quadrant. Cosine of theta is negative 15 over 17. Then which of the following is the value of tangent to theta? Gotta have a picture, right? So we draw this. We know our angle is in the third quadrant, so we place it into the third quadrant. 1, 2, 3, 4. And we can sketch our angle here. This is theta. Now we know that our angle is going to have a point on the terminal side, which has an x and a y coordinate. And because we're trying to find the trig functions, we're going to use sine as y over r for an angle, opposite over hypotenuse, y over r. Cosine is x over r, because that would be the adjacent. And tangent is opposite over adjacent, so y over x. So we need to have the x and y values and also the r value. So which of the following is the value of tangent of theta? All right, well, to find this one, we have to use our given information. So we know that cosine of theta is negative 15 over, let me put that negative sign out front. We know that it's negative 15 over 17. We also know from our formula that cosine is equal to x over r. And we have to decide which of these does the negative sign go with, because we know it's either negative over positive to make the whole thing negative, or positive over negative to make the whole thing negative. And what we said before is, if you think about plotting this point, you're going back on the x-axis, so you know the x-coordinate has to be a negative amount, because you're going backwards. So this is going to be negative 15. You also know, because you're going downwards, that the y-coordinate is going to be negative as well. Finally, because r is the distance, it's the radius out to this point, r is always a positive number. And so r must be positive 17. And so let's make a note here. R is always positive. And the only way you can tell with x and y is you draw the picture and you see if you're going in a negative direction for both, and we are this time. All right, so for y, let's see. How do we calculate y? Well, for y, we've really got a triangle in disguise. We went back here on the x-axis, we went back 15 units. We know the radius out to this point is 17. We've got no idea what the y-coordinate is. If you know two sides of a triangle, you can always use the Pythagorean theorem to find the third side. So we'll do a squared plus b squared equals c squared. Now c, this time, we know it. The hypotenuse is 17 squared. So we'll do y squared for a plus 15 squared for b equals 17 squared. And this is another common one that I happen to have memorized. So y squared, and then on your calculator, 225 equals 17 squared is 289. Subtracting these gives you y squared equals 64. And taking the square root of both sides gives you y equals 8. So you're tempted to put 8 here as your coordinate, but remember, because we're in the third quadrant, it means your y-coordinate is going down, so it must be negative 8. So let's just check our signs one more time. We went backwards in the x direction, so negative. We went downwards in the y direction, so negative, and r is always positive, so that looks good. So which of the following is the value of tangent to theta? Well, tangent is y over x. So we'll do y over x. Negative 8 over negative 15. But the negatives cancel out, making this positive 8 over 15. I should have given you guys more room for this. Sorry about that. Sine of theta is going to be y over r, so negative 8 over 17. All right, so you've got some practice problems ahead of you to work on. So let's take a look through and see where we want to get up to. So problem 1, you should do. Problem 2 is a checkpoint. Problem 3, you start to figure out some stuff about the signs. Sometimes things are positive, sometimes things are negative, and that's a pretty good puzzle for this one. So please do these practice problems on your own. Okay, we're going to take a look at practice problem 1, just to review it and make sure you got it correct. So let theta be an angle in the fourth quadrant with tangent of theta equals negative 4 over 3. So we draw an angle in the fourth quadrant. So this is theta. We know that there's some coordinates here, so we have an x and a y value. And those aren't fractions, those are just labeling. We also know we've got a radius out to the point, so this is some r value. Now, tangent to theta, according to our new formulas, we have sine is the y-coordinate over the r value, opposite over hypotenuse. Cosine is x over r, adjacent over hypotenuse, and tangent is opposite over adjacent, so y over x. So we know that this is our y value, and this is our x value. So we have 4 and 3, but we also know one of them is negative in order to get to this point. So let's think about it. We go 4 in the x direction, it says, and then 3 down in the y direction, so we know that the y value has to be negative. Finally, to get the cosine, we know that we need the r value as well, so we're going to do a Pythagorean theorem, a squared plus b squared equals c squared. So we plug in 4, we get 4 squared, we plug in 3, because the length of the side is still 3 even though it's 3 down. So it's 3 squared, and we get c squared. And c is really the radius out to the point. So 16 plus 3 squared is 9 equals r squared. 25 equals r squared. Square root of both sides, r equals 5. Okay, so now we're ready to write down our two answers. We know that cosine of theta is equal to x over r. So we do x over r. And hopefully we got the right signs. Let's just make sure. X is positive because we went to the right. R is always positive because it's a distance, so 4 over 5 is correct. Whoa, okay, wow. I actually made a pretty big mistake in this problem, guys. Sorry about that. Let's go back and fix it. So here we labeled y was 4. So this should have been a 4. Here we labeled x was 3. This should have been a 3. Sorry about that. And it's still negative here. And even if you switch these values, 4 and 3, 3 and 4, you still end up with 16 and 9, you still end up with 25, you still end up with 5. So that's still right. However, we have to go back here and fix this for cosine. So cosine of theta was supposed to be x over r, and now that we've updated the value of x, it should be 3 over 5. I'm really sorry about that. So here we go, 3 over 5. Sine of theta is going to be y over r, so that's going to be negative 4 over 5. And so remarkably, even though we couldn't find these angles in right triangles, we can still write down their sines and cosines. So the next one I'm not going to review because there's a checkpoint. Problems 3, 4, and 5 are really nice if you've done them because they start to let us to think about the next thing, which is identifying the sines of angles. So if we want to identify the sines of angles in the coordinate plane, then let's write our new formulas below. We know that sine is always y over r, because if we think about angles in the first quadrant, and we have theta here, the y value is always the opposite over the hypotenuse, which is always r. The cosine of theta is always going to be the adjacent value divided by r. And tangent of theta is always going to be y over x. So we're going to try to make some predictions about the sines, and it's a little bit ambiguous here. We're using the word sine to mean here positive or negative, but we're also using the word sine here to mean this ratio y over r, so they sound the same even though they mean different things. So the following diagram we construct will help us to remember when certain trig functions are positive or negative. So let's say we had an angle in the first quadrant. The x-coordinate is going to be positive, and because we're going up, the y-coordinate is going to be positive. And because we're going out to this radius, the radius is also going to be positive. So because x, y, and r are always positive, let's see what happens. Sine of theta is going to be y over r, a positive divided by a positive. It's going to mean that the whole thing is a positive number. Cosine of theta is going to be a positive, because x is positive, over r is positive, so cosine of theta is positive. And here, if we have tangent of theta, that will be y over x. That's a positive divided by a positive, so tangent of theta is also always going to be a positive. So what you'll notice is in the first quadrant, all are positive. Okay. Let's see what happens in the other quadrants. If we flip things to quadrant 2, in quadrant 2, our x-coordinate, because we're going backwards, our x-coordinate is going to be negative, and our y-coordinate is going up still to get to that point, so that's positive. We also know that r is always a positive number. So let's think about, in addition to the signs that x, y, and r have, the signs that our trig functions will have. So in quadrant 2, let's see what happens. Sine of theta is equal to y over r always, so y over r, positive divided by positive is positive. cosine of theta is equal to x over r, so a negative divided by a positive. That's going to be a negative number. And tangent of theta is equal to, let's see, y over x. So positive divided by negative will also be negative. So something unusual happens here. Because of that negative for x, only sine of theta is positive in this quadrant. Okay. So I think it would be useful for you guys to go through and do the same thing here, where you have a negative and a negative. And then here in this quadrant, oh, we already used pink. Running out of colors. Wow, really running out of blue. Okay. Here in this quadrant, we have a positive for x and a negative for y. And remembering that the r value is always positive, you can actually figure out some similar conclusions. But the lesson is running a bit long, and so I want to jump to those punchlines. In this quadrant here, in quadrant 3, you'll find that only tangent is positive if you do the same type of calculations. And in quadrant 4, you'll find that only cosine of theta is positive. All the other ones are negative in quadrant 4. And so this can be a lot of information to keep track of. But what we found kind of as a pattern in math is that once we derive a big result like this about the signs of things being positive or negative, we can often just remember them pretty easily, or use them pretty easily. So here's how we actually use what we just derived above. So there's a common mnemonic for helping us remember which things are positive in each of the quadrants. So in the first one, all of them were positive, so we put a big A there to stand for all positive. In this quadrant 2, only sine was positive, so we'll put a big S there to mean that S is the only positive one. In quadrant 3, we found that tangent of theta is positive, so we put a big T there for tangent being positive. And in quadrant 4, cosine is positive, so we put a big C here for cosine being positive. And this will always be true. Here, all of them are positive, sine is positive, tangent is positive, cosine is positive. And so remembering this picture actually gives us everything we need to know. So here's a common way to remember that. For problem 3, let theta be an angle whose terminal side lies in quadrant 4. Which of the following trig functions are positive? So we have, and this is like just a silly way of remembering it, all students take calculus. Because we're in the 4th quadrant, only cosine is positive. All right, so you guys have some checkpoint problems ahead, and you should pause now and give those a shot, but I'm also going to review them, so if you're finding yourself a little bit challenged with the material, you can keep watching. So let theta be an angle whose terminal side is in quadrant 2. Which of the following trig functions is positive? Well, we have all students take calculus. We're in the S quadrant because you're in quadrant 2, so sine must be a positive number, and all the other ones are negative. Let theta be an angle whose terminal side lies in quadrant 3. Which of the following trig functions are positive? So quadrant 3, all students take calculus. We're in the tangent quadrant, so only tangent will be positive. And let theta equal 300 degrees. Which of the following trig functions is positive? I'm actually going to let you guys figure this one out as a checkpoint, and I'll show you problem 4. Let theta equal 130 degrees. So here would be, whoa, that's not 90. Here would be 0 degrees. Here would be 90 degrees. Here would be 180 degrees. 130 is going to be somewhere between 90 and 180. So we're here. So we're in the 2nd quadrant. So all students take calculus. So we know that the sine of 130 degrees is going to be a positive number because we have the S, so it must be sine. All right, guys, this is a big lesson. Next lesson will be a little bit shorter because this one was so long. The good news is that you can always pause, rewind, and you can go back. So the big ideas in today's lesson were, we derived, based on SOHCAHTOA, if we looked at angles in the 1st quadrant, we saw that opposite was actually always the y-coordinate, adjacent was always the x-coordinate, and then the distance out to the point was always the hypotenuse, r. And so by looking at this, and making the transformation that y was always the opposite, x was always the adjacent, and r was the hypotenuse, we got 3 new formulas for sine, cosine, and tangent. And these 3 formulas turned out to be really useful because angles that are outside of the first quadrant all have x, y, and r values. So these formulas unlocked finding the sine of those. Now what we saw is that sometimes when we're in these quadrants, instead of always getting positive numbers, sometimes we get negative numbers. And it can be a lot to keep track of whether we're going to have a positive or negative number for our answer. So to keep track of the signs of our answer, we can use a mnemonic which is all students take calculus, and this will tell us which ones are positive. So here, because it's t, only tangent of theta is positive. And then here, this one is all are positive. All right, so we're going to look more at how we combine these ideas in the next lesson, but I hope you guys found this lesson useful, and I'll